Please welcome Felgentreff. Tim Felgentreff.
Tim, yeah. Hi, okay. So this talk's going to be about Topaz, which is a pretty new Ruby implementation, which I've been working on with Alex Gaynor for the last 11 months, roundabout. But we revealed it 6 weeks ago, so you may or may not know what it is, or may not clearly know why we did this, or maybe you've already played with it, maybe you've already contributed. Regardless, I'm just gonna tell you what it is anyway, and if you know, that's good. So Topaz. Topaz is, first, it's a Ruby interpreter. It has a custom bytecode set that it interprets, and that's just pretty standard. Parsing Ruby, compiling Ruby into bytecodes, interpreting those. That's fine. That's easy. Everybody does that, right? Now, the first little thing is it's written in RPython, and this kind of is Python, but isn't quite Python. But I'm going to get to that later. So we have this interpreter that's written in a kind of Python, and the cool thing about this kind of Python is you can translate this kind of Python into C and then compile it. And what that gives you is a pretty fast binary that already does quite a good job at running Ruby. That's awesome. And the real cool thing about RPython is that RPython is actually the implementation language that powers the PyPy Python implementation that has if you've ever done Python programming, you may know that PyPy has a very, very good JIT. And this JIT we inherit for free. And it's not actually the same JIT because PyPy doesn't have like this one JIT and you can implement other languages on top of Python and then you reuse the JIT. No, when you translate an interpreter into C using RPython, RPython can actually generate the JIT for you. That's specifically for your language. And it can do a really good job at accelerating exactly your language. So Ruby code like this, where we are running in a loop this comparison, maybe implemented in Python code like this, that does a bunch of work trying to figure out what kind of classes we're dealing with. And you can already run this Python code on a Python virtual machine and basically have a real Ruby that runs on top of a full Python VM. You can translate this to C, and then it gets really long, and I couldn't actually fit the whole code that just for this. That's all the same. That's the same method. So this method comparator gets transformed into this C function, and I couldn't fit it on the screen. This is just the first part of the declarations. But it also generates a JIT for that method, or some JIT information at least. And so while executing that Ruby code, the Topaz VM will at some point decide, hey, I'm gonna trace what you're doing here, and it will realize that you're running this method a bunch of times, and then it will see, oh, great, I already have some information about how to speed this thing up, how to generate machine code for this. And it's going to do that and speed your Ruby code up, just like that. So while there's been a lot of confusion about this, so while Topaz is written in RPython, and while RPython also powers PyPy, it is not a VM that runs both Ruby and Python. There's been confusion on Twitter about that, whether now suddenly we have a VM where Ruby runs on top of Python, or we have something where you can mix the two languages. It's not like that at all. It's just only Ruby. It's just a Ruby VM. Why? Why another Ruby VM? We already have so many VMs, and like JRuby and Rubinius have taken years to get to a point where they're actually usable. Why would you create a new VM? And oh, I should have mentioned that. So most of the slides are going to be in my handwriting, but because that's stuff I want you to take away from me. But everything that's actually printed is stuff I stole from somebody else, and he may or may not want you to take that away. But that was in the IRC log, so Alex should have, if he didn't want people to know that's the reason why we did Topaz, he should have written that. So yeah, the reason to write a new VM is just because it's fun and because we wanted to see whether our Python can do it. And before Topaz, I'd actually never worked on a Python project before. I like coding in Ruby or Smalltalk, but Python has never quite been my kind of thing. So how did I get in there? 11 months ago, I talked to the guy on the left, Karl Friedrich Bolz, who's just now finished his PhD on some of the meta-tracing JIT optimizations they do in PyPy. And he said that our Python is this really great language to write interpreters in. So I tried it, and I wrote a little functional language, and I thought, wow, this was really easy and really quick, and it's already really fast just because it generates the JIT for me. And then I thought, Ruby could really benefit from this kind of technology. So I went to him and asked, does anybody do Ruby on PyPy? And like 2 weeks earlier, Alex had committed the first bunch of code to Topaz. So we got in touch, and that's how I ended up on the project. So I said earlier that our Python isn't really Python. So I'm technically still not working on any major Python project. I'm still not using Python. And the reason is because our Python is this restricted subset of Python that is amenable to static analysis, which is necessary if we want to be able to transform it into a language that we can statically compile, like C. And because being our Python isn't really well defined, what the RPython translation toolchain does, it analyzes your whole program, everything it may do, every path it may take, and then it either decides, yeah, I can prove enough about this program so I can convert it to C, or it decides it can't. So it's very hard to tell for any one program whether it's RPython or not, or which parts aren't RPython before you actually try to translate it. But what this means in practice is that most of the Python standard library is off limits for you. You're not going to be able to use that because it's just too dynamic to be analyzed and compiled down to C. So I just take RPython as being this language that kind of looks like Python, but it's just really a language that's neat to write interpreters in and helps you with that. And if you ever, after this talk or sometime later, want to contribute to Topaz, here's a little map of what it currently looks like. And there's nothing really exciting in here. Like any other interpreter, you have kind of your object space, which you start at, where that creates your nil object and true and false and all these core objects. And you kind of have these core classes that are created before you run any Ruby code. You have your lexer, parser, compiler over there, and a bytecode interpreter. And this little, can you see the cursor? Yeah. So, and this little cloud is, I'm intending to make this bigger because that's the part of Topaz that's currently already written in Ruby. Because what we found is that Topaz already does such a good job at optimizing Ruby code that we can write large parts of the core library in Ruby. And you've probably heard that before about the Rubinius project. And we're still at a very early stage. So we may or may not eventually find that we have to move stuff over from Ruby to Python or vice versa. But we're not quite in the same position because already we have some code that is faster if you implement it in Ruby than if you were to implement it in RPython and compile it to C. And I'll get to why that is. Question? No. Yeah, thanks, Toby. So what's the current status? So when I prepared those slides like a week ago, we passed around 5,000 Ruby specs. That's mostly core. If you're familiar with the Ruby spec project, you have core, command line specs, library specs, and language specs. And those 5,000 expectations we pass are mostly core, some in language. And the reason is because we haven't actually copied the Ruby standard library over into our tree yet, so we don't run those specs. And even in the core, we're still missing so many methods and so many corner cases. But RubySpec has been very helpful at getting this thing up and running. So if any of you ever contributed to RubySpec, thanks to you. And everybody else, if you ever find something that's weird in Ruby and there isn't a spec for it, go add one. That's really helpful for new implementers. So running 5,000 Ruby specs isn't much. For comparison, Rubinius passes like 150,000 expectations. And I'm saying to you that we're really fast, and you probably heard that before from the JRuby guys and the Rubinius guys and the Maglev guys, and pretty much everyone who tried to implement Ruby and ran benchmarks before they did anything interesting, like run Rails. So what we did, we checked back with Evan and Hedius from Rubinius and JRuby to find out what the hard problems are when implementing Ruby. And with hard problems, we mean stuff that makes Ruby implementation slower. So, for example, capturing the full binding to be able to do a binding eval or just do an eval in a block context. That's fairly expensive for some implementations, so we implemented that. Didn't really lose much. Set trace func, pretty expensive, and object space each object isn't actually even activated on JRuby by default. We have those. Constant invalidation. Hedius felt that that's kind of hard, so we made sure that we're right in that part. So we implement these features from Ruby, and we're still very fast, which is nice. However, for good benchmarks, we're still missing so much. We don't do any encoding support. So any benchmarks you may run on Topaz, or I may run now later on Topaz, that does anything with strings is really skewed in our favor, because we don't do any encoding checking or any conversion or anything. We don't have threads, but in our Python, there's a branch that may help us adding proper native thread support automatically. There's a branch where we are working on getting fibers ready, and we don't have an FFI or support RubyC extensions, of course, but we're not sure how we're going to do that yet. So there's some open questions that are rather large. And currently the source tree is 15,000 lines of Python, 2,500 lines of Ruby, just to get like general feel how big this project is. And that's actually quite a bit of Ruby. And I was surprised when I ran those slug counts that we actually have that much Ruby compared to Python. And the benchmarks are pretty nice. So I'm gonna switch over into demo mode. And probably have to close it. And yeah. And first I'm gonna run this really, can you hear me all right still? Yeah. Okay. This really stupid benchmark that just does like this while loop and the diff mod and then increments I. And actually I'm gonna run this on JRuby first, because JRuby is the fastest other implementation I could find to run this benchmark on. And it takes quite a while. It takes about 4 seconds. And this actually isn't the kind of Ruby code I ever write. I never use while. It's just feels wrong. That's just not normal. And I probably wouldn't write that kind of Ruby code either, but I probably would use each for iteration, right? And if we do this on JRuby, what we find is that JRuby is really good at optimizing loops that it can represent in Java as well. If it has to do stuff like create a block and pass that block somewhere, it gets slower quite a bit. So I'm going to see how we do, Topaz does, on this tiny benchmark. And of course, I know that this is not going to work, because I've reserved a little bit of time in this talk to show you how I would go about and implement a method such as fixnum divmod in Topaz. So, okay, so the first thing I would do is like find out where's divmod implemented. Okay, and I'm not on the right Ruby. And I'm like, okay, big decimal, see numeric divmod. Okay, I'm going to see numeric divmod. And then it just says, okay, this just returns an array of the quotient and the modulo. So, okay, so I have to implement this on numeric. Fine. Then I'm going to look whether Python already has something like that. Turns out Python already has a built-in function divmod. And I'm going to try and use that one. Oh, first I would probably check whether it does the same thing as in Ruby, but it does. Okay. So ignore that it's called RuPyPy on my machine. Before we had a name, it was just RuPyPy, and I haven't bothered to rename it. So in RuPyPy, if you clone the Git repository in Topaz, sorry, you'll find a structure with much less temporary files, and you're going to find all the interesting stuff in the Topaz directory. And if you want to look for class implementation, you're going to have to go to objects, of course. And before we called fixnums, we called them ints because we didn't do the hierarchy right, so it's still, the file is still called int object. And there you have a class like this. You have fixnum object, and that implements the fixnum Ruby class. That's a Python class that will implement the fixnum Ruby class. That inherits from a other Python class, the root object. But you know, because of course you know that in Ruby fixnum inherits from integer. And we can have that. We can have different hierarchies on the Python side and on the Ruby side for reasons of efficiency. So on the Ruby side, it will look like fixnum inherits from integer object, because I say here, the class definition for fixnum is that it inherits from integer object, but I'm actually inheriting from the root object directly. And if we go down, I can try and implement divmod like this. And every Python implementation of a Ruby method takes a space as the first argument besides the self. One of those reasons why I don't like Python, actually. Stupid self. And we know that we have to take another argument, so we have to something like other. And this decorator here says expose this method divmod as the method divmod, just divmod, on fixnum object. And it can also has some neat convenient stuff for doing automatic type conversion. So you can say other, I expect other to be an int. And what this will do is whenever this method is called from Ruby, it will send the first argument through this int method here automatically for you. So it will check whether it's a fixnum, and if it isn't, it will call to int on it, which does the right thing most of the time. And now we can just say something like, okay, so we get an integer object now, a Python integer object. We can say divmod self int value other. And that will return a Python tuple with Python integers, which is not what we want. Instead, we want a Ruby integer for every integer that's in the Python tuple here. So this is Python list comprehension. For people who haven't seen that, that's just saying for every I in whatever this returns, return me one object like that, or do that. And this will again create a Python array, which is still not what we want, so we have to also wrap this thing in a Ruby array. And you already see that a lot of stuff goes through object space, and object space really is this one big class that you're going to have to look at if you ever want to contribute, because pretty much everything goes through there somehow. So that should be it. So let's see. Let's go back to the benchmark, and maybe just because I'm going to run this interpreted, I'm going to exit early. So I said earlier you can run this whole Python code just on a Python VM. This is going to be slow, but it's nice for testing. And that returns something. And did it return the same thing as Ruby would? Well, yeah, kind of. Our inspect string is wrong, but we'll say that's fine. But as a matter of fact, that isn't fine at all, because as it turns out, in Ruby, you can pass not only fixed nums, you can pass big nums, floats, and there's some really weird behavior on how divmod behaves if you pass stuff like infinity. So instead, I'm just going to implement this in Ruby, and I've already done that. And it's just going to look like this, because this does the right thing. And it's much less code, and it's in Ruby, hey. So this is the other place you're going to look at, is libtopaz. This is the kernel directory in Rubinius. And here we have plain old Ruby files. Oops, that just Ruby code, and that Ruby code is just loaded at startup. And the good thing about implementing stuff in Ruby rather than in Python is you don't have to analyze the whole thing, convert it to C, and compile it again. Your Ruby code you can just add, and then it will run with the compiled version of Topaz. So now we should be able to run that benchmark again. Oh, shit. Pardon me. So JRuby took, what, 4 seconds and 6 seconds, right? So let's see, 1 second for the while version. Let's see this one. Oh, hey. So what can you take away from this one? So first, we're faster in this occasion. The second, and in my opinion, more important thing is the Ruby code isn't, the more Ruby-ish code isn't slower than the more Java-y code. And why is that? Let's take a look at what. How many minutes? 6 minutes. Okay. Let's take a quick peek at what the JIT actually does with this. Log. I'm going to call this JIT log. So you can, if you run Topaz, you can set the PyPy environment variable to see a bunch of things like GC stats and JIT stats. If I run this again, I have a file called jitlog. And you really want, if you're using Emacs, you really want PyPy trace mode for this. And then you can search backwards. And the last thing that gets executed is our loop. And you already see from the number of debug things here, that's all stuff that's not actually executed. That's just for me, so I see what's going on. And maybe I can fit the code over here. So let's see what's going on. So in every loop, it's loading some kind of local variable. And after JIT, it's just checking that this local variable is still an integer. So this is just one operation here for loading the local variable. Then it loads the self, but the JIT already sees that we're not using the self, so that's a no-op, and it does a send. That doesn't really do anything. And that send is actually checking that we haven't reached the end of the iteration. And because the JIT knows that we're dealing with integers here, the integer less than comparison, the fixed num less than comparison, ends up being just an actual integer processor less than comparison. So that's pretty fast. And the block's removed completely here. That's completely inlined because we're not doing anything fancy with the block, and there's nothing interesting here. So what we end up here is that's already the inline diffmod method. And that goes down until here, I think. Yeah, until here. So this is all just integer operations, and it's inlined, and we're not actually creating a block. So that's why we're faster in this instance than JRuby, because the JIT that our Python generated for us can learn so much about what we're executing that it can break everything down pretty much to the lowest thing that the processor needs. And this trace isn't going to look any different in the while loop, because it's really literally just the same. It's just checking whether the iteration variable is still smaller than what we want to end up at. So this is just a very, very quick overview over what Topaz can do for you. Takeaways. Oops. So by now you learned that we want to be the fastest Ruby implementation. And I think even after we implement lots of other stuff and we run Rails, we're still going to be the fastest. And for the micro benchmarks we run, currently we are, but you know, lies, big lies and micro benchmarks. But to get to a point where I can run benchmark on Topaz and see that Topaz is faster than any other Ruby out there, and say that I believe Topaz will be faster than any other Ruby on anything, we're going to need a lot of help. So if you're interested in creating a Ruby VM or looking at how it's done, or if you try to run your Ruby code and something doesn't run, or if you run Ruby code and something is slower than on any other virtual machine for Ruby, open issue, open a pull request, contribute. We're happy to have new contributors, and it'd be great to have more people. So some information, we're on the Topaz Freenode channel. You can follow Topaz project or for news. Here's the Git repository and the website, and down under the line, that's my Twitter account name and my IRC name if you ever want to ping me in Topaz. Okay, thanks.
Thank you very much. Any questions? We got a few more minutes left.
I guess that Rubinius might be a good source of code for Topaz. How costly, time-wise, and how difficult it might be to get the source from Rubinius to Topaz?
So Rubinius, the kernel, the core source code that's in kernel, that has 3 different subdirectories: core, common, bootstrap, common, and delta. And the idea was originally, when they were still trying to share code with maglev, that in common there's not any Rubinius specific code, and you could just take that. But right now, if you grep for rubinius.primitive, you'll find that I think the only files that don't have Rubinius primitive are true RB, false RB, and dir19 RB. And those we copied. Those work fine. But the others are going to be a lot of work. And we've talked to Brian and other people, and the maglev people are still interested in sharing more code with Rubinius. So we may start a refactoring of that core code at some point so we can share more, which would be awesome.
Regarding the benchmark, when you benchmarking on a chitted VM, I would advise you to not use wall clock time benchmark. I would love to see Topaz being the fastest because I'm a Ruby programmer. But please use operations per second, for example, where you could warm up the VMs or where you could warm up the cheating. And also, one question: how does Topaz performs over time? I mean, if you have a big application running and the request pattern changes, so does the chit apply to that, or does the chit
yes,
does something for that?
The JIT never stops watching your execution. So if you run a million loops in one thing and then the state of your web service changes or your request pattern changes, it will optimize. It will still start optimizing new stuff. Just that it's the JIT works completely differently, but yeah. Yeah, it never stops, yes.
I have a question. Could you roll back to the slide where you had the hard problems to solve? Obviously you have much of the same problems that PyPy does itself, but why are those hard for Topaz to solve?
No, those aren't hard for Topaz to solve. Those are hard problems for any Ruby implementations to solve to be fast.
The next one that you have done, so the one that says FFI, yeah, why are those hard?
Because it's hard to find a balance between what you're going to allow in a foreign function interface or in an interface for the Ruby C extensions and how fast you're still going to be. So on JRuby, they deprecated the C extension interface again because it's really hard to stay fast if you're running C extensions because you have to do a number of trade-offs, the stuff that you can't optimize anymore. Yeah, a chance, but it's still a hard problem because people aren't gonna. if we find out that we have to do things in a specific way to stay fast, Ruby programmers aren't going to say, "Oh yes, I'm going to rewrite all my C extensions for Topaz because I love Topaz so much." That was the original idea behind the Ruby FFI, and that never worked. So.
What was the coolest thing that you learned from doing this project?
I learned to trust in the power of meta tracing JITs.
So I heard a lot that there are problems with current MRI, that it's not well documented. I wanted to ask if you had some problems that documentation wasn't enough and you had to read the source code.
MRI source, okay, many things in MRI are really strange and not well documented, that's right. And MRI source code is sometimes hard to read and hard to understand. But I found that when there's something I don't understand about Ruby behavior, I read Rubinius source code. And that's very well documented. And they document why they do stuff in a specific way with like, oh, quirk, this is how MRI does it in this case. And yes, yeah. Yeah, I rely so much on the work that Rubinius guys have done with RubySpec and with Rubinius, so they're great.
Is Topaz shooting for 1.9 or 1.8 as well, or just 2.0?
Just 1.9 for now.
One more question.
In my opinion, this benchmark was artificial, but too much artificial, because the optimizers in compilers, which are present in JIT compilers, may optimize code the way that they actually compute they do all the computations at the compile time. So you can get crazy results. And if you did this benchmark and you provided some input from some environment variable, for example, and you randomized the content of the array, which was the input, you'd get different results. And what I would like to see in those artificial benchmark is data dependency, because this is the most hard part. I did some benchmark on PyPy, and in some benchmarks, PyPy loses to Python in this matter. So that's just my small comment. Thanks.
Yeah, the benchmark wasn't meant to be a very good benchmark. It was meant to be small enough so I can quickly talk about it while showing the JIT log actually. So sorry about that, but there's a good benchmark suite that's called the Meta Tracing VM Experiment. That's on GitHub. It's by Lawrence Tratt, who did the Converge VM, if you know that. And he has a bunch of larger benchmarks that also use input from the outside. And currently, I'm trying to get those running, all of those running on Topaz. And the ones that currently run are all faster than JRuby, except for the stupid Fibonacci example. So I'm trying to get to all of those running and all of those faster than any other Ruby implementation. But yeah, you're right. There should be outside input in benchmarks. That's right.
All right. Thanks very much.